Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 2, IP Routing Fundamentals. And as you can see on the whiteboard, we are going to look at some very fundamental principles of IP routing here, and they're very important principles because, as I often say, the most important study you do in Cisco is of the fundamentals. It's when you're studying for your CCNA, when you're studying for your CCNP, and you are nailing the fundamentals down. Because if you don't understand on a basic level how things work, there's no way you'll ever understand the intermediate and the expert levels, particularly when you're troubleshooting. If you don't know how things are working when they're working correctly, there's no way you can be expected to fix them in a production network or on an exam when they're not working. So we're going to take just a few minutes here to discuss what a routing protocol is in the first place, or even just what a protocol is. You hear that all the time, but what exactly is it? We're going to take a look at a basic routing table operation, or actually several of those, one of them in our production network and several mock ones, because it's important for you to see how a routing table makes the decision about what path or paths to enter into its routing table. After that, we'll take a look at static routing, and I know that you learned this in your CCNA studies. You think you've got it nailed. You still need to pay attention to this video. It's not something you want to skip, and it's a vital real-world skill as well. And you need to be able to troubleshoot static routing. You may get some returns on pings occasionally that you've not seen before, but if you've seen them in this course, then I've done my job, and you'll be ready for it in the real world. And finally, we'll talk about floating static routes. That's a great name. You know, what are they floating on? We're going to take a look at that very shortly, but first, let's discuss that routing protocol that we were talking about, or actually what a protocol is to begin with. A protocol, basically, or simply put, is a set of rules. You hear occasionally about a violation of international protocol. Basically, when two countries are communicating, we've all got different cultures, we speak different languages, we've got to have a set of rules for how we're going to communicate. And that's what a protocol is. A routing protocol, the official definition, or an official definition, is a standard procedure for regulating data transmission between computers. That's a formal way of saying it's a set of rules. It's a set of rules about how two computers have agreed to exchange data, or two routers, or two switches, two devices on a network somewhere. Now, the protocols that we work with primarily in the CCNA and CCNP course are our routing protocols. And you want to keep routing protocols separated from routed protocols. You don't pronounce them like that, but I like to say it that way just so you'll catch that we're talking about two totally different things here. The routing protocols that we use, RIP, both versions, IGRP, EIGRP, OSPF, the sole purpose of these protocols is to determine a path. How do we get from point A to point B? That's what a routing protocol is all about. The routed protocols are the protocols that are actually carrying the data. And when it comes to multiple choice questions on your exam, I think this is more a CCNA area than a BSCI area, but you still want to keep your eye on that. And don't read the question too quickly. If they're asking for you to list routing protocols and you list routed protocols, you knew what you were talking about, but at the same time, you didn't get the answer right. We're not going to do that. So that's just a quick review of what our routing protocols and our routed protocols are all about. You remember, of course, the difference between classful protocols and classless protocols, these somewhat regrettably named classless protocols. We've got classful protocols that do not support variable length subnet masking. If we configure subnets with these protocols, we're never going to see any other kind of mask outside of a /8, /16, or /24. And that's RIP version 1 in IGRP. Classless protocols do support VLSM. RIP version 2, EIGRP, and OSPF all support variable length subnet masking. Auto summarization, the official word from Cisco is that really all routing protocols in a way perform auto summarization. Because if you have routing protocols say with RIP version 1 or IGRP, that are going across a classful network boundary, then that's actually performing auto-summarization. But the way they mention it in their books and the way I'm mentioning it to you here, it's RIP version 2 and EIGRP you have to be careful about, because there's no RIP version 1 and IGRP don't really auto-summarize because they're summarized to begin with. They have no VLSM support. And I know you recall from your CCNA studies how auto-summarization works. When a route is advertised across a classful network boundary, it's automatically summarized. We turn that off with no auto summary. We're going to work with that when we work with RIP version 2 as well. If you're a little fuzzy on what auto summarization is, we'll give you a quick reminder at that time. But almost every time you even configure RIP version 2 in EIGRP, before you even name the networks that you're going to advertise, you're already typing no auto summary. And you can't turn that off with RIP version 1 and IGRP. Taking a look here in the top part of this whiteboard, we're going to put up some different routing tables, and they're not going to be routing tables that you will ever see in a production network. And the reason for that is we need to know how the router chooses the exit interface where it's going to send a packet when it is received. Because a router gets a packet, it may be destined for a local network on that router, but it's probably not. And then the router's got to decide, well, where am I going to send this next? And to truly understand how a router operates, and, not coincidentally, to pass the BSCI exam, we've got to be able to look at a set of routes and determine which one would be used. And I've put up here the criteria order for determining what the best path is. And the first one is the longest match, or you hear it called the longest prefix rule, the longest match rule, doesn't matter. You're looking at something like this. We're going to put up 3 different exit interfaces. And we're going to decide each time which exit interface it would use. If a router had to send data to any host on the 172.10.10.0 network, the first one it's going to choose is the one with the longest match, the longest prefix mask. And here it's very simple. As long as you know the order of the rules, these are simple questions. Because in this case, it's going to choose serial 1 as an exit interface, because it has a longer prefix. It's got a /28, and /28 is certainly longer than 25 and 27. But we could be looking at a scenario, and again, hopefully your network doesn't look like this. I would look for this only on exam questions. Let's say that you have this scenario. And in this scenario, we have 3 matches for the 172.10.10 network. They all have 25-bit subnet masks set, and they all have different exit interfaces. Which one is going to be chosen? This is where administrative distance comes in. And administrative distance is simply the measurement of a protocol's believability. And you remember these codes that you were so worried about in the CCNA, but you nailed it. The O indicating an OSPF route, D indicating an EIGRP route, and R indicating a RIP route. Now this is where administrative distance comes in, because there's a tie on the longest match. So now we've got to look at a lower administrative distance. And again, the AD is the measure of a protocol's believability. The lower the administrative distance, the more believable the protocol. So you know from your studies that OSPF routes have an administrative distance of 110. EIGRP routes have an AD of 90. That's an internal EIGRP route, and you'll be exposed to external routes when we talk about EIGRP specifically later in the class. And then finally, RIP has an AD of 120. So the path here that would be used in this scenario is actually serial 0, because it was discovered by a protocol with a lower administrative distance than the other two. Of course, you would not see these three routes in a routing table. The only one you would see would be the EIGRP route. Now, let's say that the longest match is a tie, and the administrative distance is a tie because they've all been discovered by the same protocol. If they've all been discovered by the same protocol, then by default, they're all going to have the same administrative distance. One is not going to be lower than the other. Then you're looking at the lowest metric. And of course, the OSPF metric is cost. RIPS is hop count. EIGRP uses a composite metric. But the question at this point is simply, what's the cheapest route? If one route has a metric of 30, the other has a metric of 40, the other has a metric of 50, then the lowest metric will be used. And where do we see the metric then in the routing table? Let's bring up a live router and take a look at this. And at the bottom of this output, it's a very simple RIP routing table. We can always see just the RIP routes, the show IP route RIP. And the administrative distance and the metric are always going to be right here in these brackets. The administrative distance we see of RIP routes is 120. The metric here is 1, because of course RIP's metric is only hop count. So that's the metric that we're looking at. With OSPF, we'd see a larger number, and of course with EIGRP, we could see a number that's 8 or 9 numbers long. But that's what's going to happen at that point, is that the lowest metric, the cheapest route, will be the one selected. So finally, we come down to the fourth criteria, and that's equal cost load sharing. And bringing our previous router screen back up, you can see that in this particular scenario, we have 3 different paths, 3 different next hop IP addresses listed to get to the 172.12.23.0/24 network. We got a next hop of 123.2, a next hop of 13.3, and a next hop of 123.3. That's because, looking at the order of the criteria, the longest match rule doesn't work because they're all /24 route masks. The lowest administrative distance doesn't work for us because they're all using the same AD. And the lowest metric doesn't work because the metric's the same. So at this point, the router will perform equal cost load sharing. So that is basically how a routing table operates and how the routing table is built. You don't see that process, and you have to run some debugs to actually see different routes come in, that kind of thing. But it's important, especially for your exam, that you know how this router selected these paths in the first place. 2 other commands I want to show you that we'll revisit several times during the course, but I want to reintroduce them to you now. And that is show IP protocols. Pardon the caps lock. Show IP protocols. This gives us a wealth of information. And we can see just about RIP, of course. We'll talk about this when we talk about distance vector protocols in a later video. But you recall that RIP sends out updates every 30 seconds. You can also see that right now we are sending and receiving version 2 only. Automatic network summarization is not in effect because I turned it off with no auto summary. Maximum path 4, this is the default. And if you took my CCNA course, you got tired of me reciting those values. But the values here for RIP, 4 paths used for equal cost load sharing by default. The range is 1 to 6, and the command to change that is maximum paths. And then finally, you can even see what networks you're routing for, and you can see from where you are receiving routing updates in the first place. So anytime you've got something, you even begin troubleshooting a routing protocol, I would strongly recommend you run show IP protocols just to get the lay of the land, see what's going on. And then finally, another command I want to show you right now is clear IP route asterisk. This will clear your routing table of all dynamically discovered routes. It's a good one to use in a production network on occasion. You should be careful with it. It's a great one to use in a home practice lab or on rack rentals because, especially if you're working with RIP, you make a change, you don't want to wait for the next update to see the result. You can run clear IP route, and if we hurry there, you can see it had already gotten those back. You could see that it got the routes 1 second ago. So that is how the routing table chooses its paths. Now when it comes to static routing, which is the topic we're about to discuss, a lot of people tend to gloss over it a little bit or just say, well, we don't use any static routing, we only use, dynamic protocols. And that's great. I do know 1 or 2 businesses out there, I've seen their networks, and they're built with all static routes. And the key here is that one day you may have to call on one of these. I've been in one, and all of a sudden you're just looking at this maze of static routes. So you've got to understand the syntax of the command to know what you're talking about and to troubleshoot static routes. But another great usage for static routing is a band-aid. When there is a problem with a dynamic routing protocol, your users still have to get their work done. They've still got to get out to the net. They've still got to have connectivity. So the ability to write a static route, especially a default static route, is a very important one. There are a couple of other reasons. If you've got a single entry and exit point to your network, you may find static routing to be a little easier on your router. And also, if you really want to control the path determination process, instead of letting a routing protocol do what we've just gone over here in the last few minutes, static routing is the way to go for that. But again, I like to use it strictly as an emergency tool instead of just having static routing for my network. This is the network we're going to look at for our static routing discussion. In our lab, we're going to see it in action, plus a couple of important troubleshooting debugs. And here, router 1 is the hub, 2 and 3 are the spokes. They're communicating through a frame cloud, and they each have a loopback interface numbered using their router number for each octet, 11112222 and 3333 respectively. Router 2 and router 3 can communicate, but as spokes, any traffic that goes between them has to go to the hub. What we're going to look at is router 3's attempts to communicate or to ping with router 2's loopback interface. Because calling our pod back up here, and we're on router 3 right now, I have removed RIP from all 3 of these. They were on there earlier for our discussion of the routing table, but I've removed those with the no router RIP command. So right now you're looking at a router just as it looks right out of the box. The only routes you're going to see are connected routes, marked with a C there in the left-hand column. These are all directly connected routes. Directly connected routes, by the way, on the administrative distance table have an AD of 0. That makes it the most believable, because let's face it, if a network is directly connected to your router, that's the most believable route to get to that network. So it does have an AD of 0. You will note, though, that you don't see any brackets here in this routing table. You don't see any brackets that say, 0/0. If it's directly connected, it's not going to list a metric, and it's not going to list an administrative distance. It's one of those little things you have to memorize, that directly connected routes have an AD of 0. So right off the bat, if we try to ping .2.2.2.2 from here, let's see if we've got any debugs running. This is a great command to see what debugs you've got running, because we're just going to run one here. It's a very important one. And I do want to remind you that when it comes to debugs, you should never practice them on a production network. You should get a rack rental service or your own home lab and debug to your heart's content. It's the way, running debugs is the way to really see what's going on when you run these commands. It's a fantastic learning tool, and it's the most overlooked learning tool that I know of, but you can't do it at work because debugs are CPU intensive, and they are by default given priority by the router even over the routing process, because it figures if you're using a debug, there's an emergency that you've got to take care of. You can have a couple of debugs going at one time and kind of forget what you're running. So the reason I wanted to show you the show debug command is this will give you a little list right here of the debugs that you are running. So let's try to ping then, looking at our map one more time. Let's try to ping router 2's loopback from router 3. And ping is our basic IP connectivity test. It doesn't tell us where the problem is, and that's where we've got to be professionals and know how to see what the problem is, because obviously there is a problem. If we get 5 dots back from a ping, that means that we have no IP connectivity to the IP address that we are attempting to ping. Now, some people will just look at it and go, well, what now? But we're going to go a step beyond that. We know the debugs that are going to show us the problem and the show commands. Because if you look in this table, there is no match for the destination 2.2.2.2. There's nothing there that's going to even begin to match that. So we've got to get a match in there. Let's see, though. The debug that I want to show you here is debug IP packet. And this is a very CPU intensive debug. Do not run this even if you need to during a high production time, because it can lock up a router. It's going to give you so much information, it'll lock up the CPU, and you're going to have to reload the router and hope everything goes well when it comes back up. So we're going to ping it again, 2.2.2.2. And we're going to get the periods again, but we're also going to start getting some messages. And you see that each one's coming back as unroutable. That indicates that there is no way for this router to even send that packet. The packet is not leaving router 3. It's not going to router 1. There's no reason for it to. There's no match in the routing table for it. So we're going to give it a match. And we're going to give it a match first off with the IP route command, and we're going to configure what's referred to as a host route. And a host route is a static route that is only going to match one destination. We use the IP route command. We're going to put the exact destination and a full mask here, because what you want to do with these, for the exam, it's a really good idea to have the IP route syntax memorized, because they might flip them around. They might put the mask in the first position, followed by the address, followed by the next hop IP, that kind of thing. You just got to be careful with that kind of question. But what we're going to do here is write a full 32-bit mask, which will exactly match 2222. So the only match for this line in the routing table is 2.2.2.2. Now, let's use iOS help to see what our options are at the very end of this command. And it looks like we have a lot of them, right? But we really don't. One of the options, and the one I like to use, is the forwarding router's address. That is the next hop IP address that you want this packet to be sent to. And of course, you better have a listing for that, a match for that in your routing table. All of the others are interfaces or interface types. Some of these you've seen plenty of times, some of these you may never have seen. That's quite all right. The key here is that if you list an exit interface at the end of the IP route command, it is exactly that. It is the local exit interface. It is not the downstream router's interface. There's no way for your router 3 in this case, to know what interface router 1's going to receive this packet on. Couldn't care less either. What I like to use here is the next hop IP address. You need to know both for the exam, but I just find this to be easier because if it doesn't work, it's easier to troubleshoot. And that's it. So now I'll run show IP route. And I've got a route that matches that particular destination. It's a static route indicated by the letter S. It's got a next hop of 172.12.123.1. And note that this one does have brackets. The first number is always the administrative distance, which is 1 for a static route. And the metric is 0. Now, if we had written this with using the local exit interface, we would not have an administrative distance listed. It would appear as a directly connected route and therefore have an AD of 0. I'm going to bring that up and show you before the end of this lecture. But keep that in mind. It's a good little detail to know that if we have a static route with a next hop IP address, the AD is 1. If we have a static route with a local exit interface listed, the AD is actually 0. So everything should be fine now, right? We're on router 3. We've got a static route using router 1's serial interface. Right there is the next hop IP address. And then router 1's going to take it from there, right? So let's send a ping back over. Let's turn our debugs off. You can use undebug all to turn all your debugs off, or I could have used no debug IP packet to turn that individual debug off. I've only got one running, so there's no reason to do that. Let's ping 2.2.2.2 and see what we get. We're getting a little bit of a different message there. We still don't have IP connectivity because we're not getting 5 exclamation points back. What we're getting is u.u.u. You won't see that one in many books. But what this indicates is that a downstream router is having trouble routing the packet. And it's sending a message back. The U is for unreachable and saying, hey, I don't know how to reach this network. Because as we'll see again by running debug IP packet and then sending the ping again, we're going to get some messages here. You can see at the end there that it is sending. The packet is leaving this router. It's a downstream router that's having trouble. And the message is coming from 123.1 saying, you know, I don't know how to get there. Here's the source, here's the destination, and that's the one coming back saying, I don't know how to get there. And the problem, of course, is that router 1 doesn't have a route for router 2's loopback either. We do a show IP route on router 1, and there's nothing there except connected routes. That's what we expect to see. So we're going to configure a static route here on router 1 as well. And it's also going to be a host route. Excuse me. That's a host route, only matches 2.2.2.2. And the next hop is going to be .2 in a moment. Because the next hop IP address is always just that, the next hop IP address, not the local address. One of the many things I really love about Cisco as opposed to, say, Microsoft, you know, a lot of Microsoft features and programs and servers will let you do something you shouldn't have done and then just sit there like, well, what do you want from me? You know, it's not going to give you a hint. Or if it does give you a hint about what's not working, it's going to give you a big hexadecimal message that doesn't make any sense. And you got to call Microsoft tech support and, you know, read that to them, and they don't know what it means either, but we won't get into that now. So, what happens though if we try on a Cisco router to list the local IP address as the next hop? The router will not allow us to do it. It's going to say first off, hey, here's why you can't use that, invalid next hop address, and then it's going to tell you, hey, it's this router. I love that in parentheses. It's like it's whispering to you, hey, you know, it's this router. Now the exam will probably not be that kind to you, and you should probably be prepared for multiple choice questions. Like I said, just make sure you have the syntax down cold. Just make sure you have that syntax down. So we'll use our up arrow to repeat the previous command, and we're just going to backspace right over that 1 and put a 2 in. Let's run show IP route. We have a static route, just like we did before on router 3. The administrative distance is 1. And let's go over to router 3 now. Run a show debug to see what we've got running. We're going to turn that off. And now we're going to ping router 2's loopback again. Goes right through, 5 exclamation points. So we were successful. Now we're going to run the debug, because it's good to know what these things look like when they're working, so you can tell the difference when it's not working. And there are messages, and all is well. Sending and received, sending and received. That's what we want to see. Now that is a host static route, and there would be nothing wrong with me having put in something that says IP route 2.200, 255.255.00. There's nothing wrong with that. It's up to you as to what you put in for the destination network and that mask. But it's always important to know how to take things off of a Cisco router. Almost all the time, and hey, it wouldn't be Cisco if there wasn't an exception somewhere, but almost every single time the way to negate an existing command on a Cisco router is simply to repeat the command with the word no in front of it. Now I know in the old days of the CCNA, they used to make you memorize about 35 different router keystrokes, and you probably never used more than one. I just used up arrow to repeat that IP route, but one keystroke I do like to use, and I think you'll find it handy as well, is to use Control A, and you'll see the cursor move to the front of that long command, and now I can just type no in there and take the route off. That saves you a lot of typing. So now I'm back in the same boat. Obviously I can't ping 2222 without a route in the routing table. And we take a look at the routing table, and that's gone. Another great kind of static route to write is a default static route. It is the route that will be used if there is no other match in the routing table. And we have the option again of setting a local exit interface or a next hop IP. I put that even on the whiteboard here because that's such an important detail to keep in mind. You're either going to list the next hop IP or the local exit interface. I personally like to use the next hop IP address. Feel free to use whichever one you prefer. So let's look at what a default route, a default static route looks like. Because the syntax looks a little odd. It's going to start, it's still the IP route command. Both the destination network and the mask are all zeros. And then we can list the next hop IP or the local exit interface. And now you see there is a little bit of a difference. There's now an asterisk next to that S. That marks it as a candidate default. Now later in this course, you're going to see some default routes with OSPF. So if you've got more than one candidate default, obviously only one of them is going to be used. But since we only have one candidate right now, that one's going to win, and that one is the default static route. Notice that the gateway of last resort, which was not set in the earlier tables, let's see if we can move up a little bit to see one of those tables. Here's an earlier table on router 1. It says gateway of last resort is not set. That's the default. But what we see now is that the gateway is set on router 3 to router 1's serial 0 IP address. So anything that router 3 doesn't have a match for in its table right now, it's just going to send it to 172.12.123.1 and hope that that router can handle it. And as you can see, it can. We left the debug on, no problem there. But you saw the 5 ICMP echoes come back, so that is a successful ping. Now there is no match in the routing table here in these routes for 2.2.2.2. There's nothing there. So what happens in this case is now there's a default static route, and that next hop IP address is going to be the one that's used. Now I'm going to take off that default static route again. I'm going to use my up arrow to repeat the command, Control A to move to the front of it. Again, that's not an exam thing, but it's a great real world thing. Because I want to show you what a static route looks like, and we'll make it a static default route here if you use the local exit interface. Because note up here that our default static route, the way we configured it the first time with the next hop IP address, it's got an AD of 1 and a metric of 0. What's this one going to look like? It's going to say it's directly connected. That's a good detail to keep in mind. It's directly connected. It's considered a directly connected route which has an administrative distance of 0. So if for some reason you need a static route to have an AD of 0, you've got to use the local exit interface instead of the next hop. Now we're going to take a look at the third kind of static route. We've got our basic static route. We can make it into a host route if we want to. We have a default static route. And now we're going to take a look at what a floating static route is, what exactly it's floating on, when to use it. And I've configured quite a few of these in my career, and I think you'll find this to be very helpful in the real world as well as on your exam. So we're going to use the same network setup here. I am going to delete a bit here on the whiteboard. We're going to keep the frame connection up between 1, 2, and 3, just like we've had. And we're going to configure that as a RIP network. So we've got RIP network running right here between 1 and 3. I'm also going to remove the loopbacks. We're not going to use those here in this particular section. What we are going to have is a separate network connecting routers 1 and 3 that is not going to be RIP enabled. So this is our RIP network, and we know it's 172.12.0.0. But we're also going to have a separate connection between routers 1 and router 3. And this is going to be the 210.110 network. And again, we're going to use the router numbers as the last octet. So this is our setup right now. I've taken all these static routes off of router 1 and router 3. And what we're going to see, let's bring up the windows then. And as you see here at the bottom of this screen, I've already called up show IP route RIP. And RIP has two separate paths right now to 172.12.23.0. And again, going through our selection process earlier, it's got the same mask length for both advertisements. It's got the same administrative distance because they're both RIP routes. It has the exact same metric, and therefore we've got equal cost load sharing going on by default. So the Ethernet segment connecting routers 2 and 3, 172.12.23.0, is reachable on router 1 two different ways, through the frame, through router 2, and through router 3. So we have a scenario here, though, where if something happens to this frame, then router 1 needs another way to get to that particular segment. And it could get there. We'll add this for the visual while I'm chatting. Router 1 could get there through the 210.110 network, but the problem is, one of the issues, is that there's no routing protocol running over 210.110 for whatever reason. And I've been in that situation. Maybe you don't have control over the other end. Maybe somebody passed a rule that you don't agree with, but for whatever reason, you can't run a routing protocol over this connection. Now what we can do is write a static route to get there, but let's see what happens if we just write a regular old static route. We come in and we write this IP route command to go to the 172.12.23.0 network. I'm going to put a 24-bit mask on it, and we'll use 210.113 for the next hop IP address. So all is well. You write that, and let's see what happened to our routing table. Well, now we've got a problem, because the static route is being used now to reach 172.12.23.0. The load sharing is not being used anymore. Remember, we had load sharing just a second ago before we configured the static route. The problem is that by default, the administrative distance of the static route is 1, where with a RIP route, it's 120. So since they have the same length mask, And then we have to look at the administrative distance. The static route is considered more believable. So you might not want this either, because now all your data that's going to the Ethernet segment connecting routers 2 and 3 is going through the 10110 network and all going through router 3. Only one path is in use. What you probably want in this scenario is to use this path over the 210.110 network only if the frame goes down. So first off, we're going to take that static route off just by putting the word no in front of it. And that should adapt pretty quickly. Let's take a look at our routing table. And the RIP routes aren't back yet, but they will be shortly. If we do a clear IP route asterisk, this is where I was talking earlier about how this can speed up the process. Getting your table updated. Now the routes are back and everything's just the way it was before. So what we can do is configure a floating static route. And a floating static route is a regular static route. We're going to use the IP route command. The syntax is the same with a twist at the end. So let's configure 23.0. So far so good. We're going to use the next hop of 210.113. And you know what always shows us the next option? iOS help. I like to use iOS help when I'm studying, even if I know the command, because I want to see what else I may be able to do. And maybe that sounds a little silly at first. Once you start doing it, you do it all the time, and you'll be amazed at how much you pick up. That's why I'm such a big believer in working on real equipment and not router simulators. Because what's one of the choices that we have here? Distance metric for this route. We can actually change the administrative distance of this route from the default of 1. And what we need to do is change it to a number higher than 120, which is RIP's administrative distance. So if we wanted to get cute and show off a little bit here, we could assign it a distance of 121. So we just wrote a static route the same way we did a few minutes ago, but we changed its administrative distance to 121, which makes the RIP routes still more believable. So now, if we look at our routing table, the static route is not there. The RIP routes are still there, because the administrative distance is now in RIP's favor, where a few minutes ago it was in favor of the static route. So let's test it. This is the joy of a home lab, because I found that when you shut down interfaces in a production network, people get really mad. We're going to shut down serial 0 and see what happens to our routing table. So we've shut it down. We see the line protocol go down. Administrative state is administratively down. Let's do a show IP route, see what happens. Do we still see? There's the floating static route. The floating static route is now in the table because the routes with the better administrative distances are gone. And you see the AD in the brackets is actually 121. So that's when you use a floating static route. It's in a scenario like this, where for whatever reason you are unable to run a routing protocol over one link, and you want to use it, but only if your routes that have been discovered by a protocol go down. So of course that's another reason why you need to know administrative distances, because sometimes you learn the stuff in the CCNA curriculum, it's almost, there's a lot of memorization there, and you're thinking, well, am I ever really going to use this? Well, yes you are. Yes you are. Because here you used your knowledge of administrative distances to correctly configure a floating static route. So now your users would still have connectivity to 172.12.23.0. But if we reopen that interface, and I'll go ahead and save while the frame has to come back up. There's the interface. The line protocol is already up. And it should have the RIP routes pretty shortly. Now that that interface is back up, the RIP routes will be put back in the table, because their administrative distance is more believable. So let's take a quick look here. And they're not back in yet. Like I said, that's one of the drawbacks of a distance vector protocol. Let's clear our routing table of its dynamic routes. Do a show IP route again. It may take a minute. Yep, they're already there. Great. And you see now that the RIP routes have returned to the table. So as I mentioned at the beginning of the static routing lecture here, it seems like a skill that you may not use that often, but I think as you go through your career, you'll be surprised how good a troubleshooting, it's not really a troubleshooting tool, but how good a band-aid static routing can be until you figure out what the problem is. The key there, I'd like to remind you, is when you do diagnose a problem and you've got the dynamic routing protocol running correctly, make sure to take the static route out before you leave.